Okay, so basically, I wanna model this system with GIFMod. So I have this I don't know, this container which is divided into two compartments with volume of V each of them. Now I'm gonna assign V to be 1 cubic meters in my model. And then I have some initial concentration in one compartment, and there's a membrane that is separating the two compartments. And then I remove the membrane, and then I want to see how the concentration changes as a result of only diffusion. And the other thing is that I basically make this assumption that the distance between the centroid of the first compartment and the second compartment is L, right? And L, let's say I'm gonna assume L is also 1 meter. Okay, so basically this is what we have. Let me just close this. So this is GIFMod. So I'm gonna represent each of the compartments as a pond. Okay, you can probably use some other components too, and it's gonna work the same way. But a pond works. So I'm gonna just add one pond. Actually, I'm gonna add two ponds. So this is gonna be each of the compartments. And then I'm gonna assume that each of the compartments is 1 cubic meters. So I'm gonna make the bottom area of pond 1. And then I'm gonna also give an initial water depth of 1. Now there will be no water flow, okay? So that's it. And then I'm gonna do the same thing for pond number 2, right? So in pond number 2, I'm gonna say the bottom area is 1 square meter, and then the initial water depth is 1. Okay, that's pretty much what I have. Then I have to basically connect them. Okay, so this connector is going to behave as our interface, right? The area interface between the two compartments. So I'm going to connect this, and then I need to give some properties to this connector. You know what? I need to provide a Manning's roughness coefficient, even though it's not going to be used. But since we are connecting two ponds, GIFMod assumes that it has to calculate the flow between the two, and it calculates the flow based on a Manning's roughness coefficient. So I'm going to just type a value, even though it's not going to matter really, because otherwise it's going to give me an error. Now I can do it without, and then you'll see that it's going to give us an error, and then we can fix it. It's not a big deal. So I'm going to just give it 0.01, and then I'm going to give an interface area. Even though if I don't give the I have to give an interface area. So I'm going to assume that the interface area between the two ponds, pond 1 and 2, is 1 square meters. Then I have to give a length for this connector, and that length is essentially the length from the centroid of the two compartments, right? Which we assume to be 1 again. Okay, so we do 1. So that's what we do is, so we got the essentially hydraulics in place. Even though there is no hydraulics, there will be no flow, but we need to do this. So basically that's what now let me save this whole thing as, I don't know, let's call it the diffusion example. Okay, then I need to add my my solute, right? So I'm going to go in order to add my solute. Now, by the way, just one thing I want to point out: there's this dispersion coefficient here, this dispersion expression, and the dispersivity. Okay, that's when, I mean, this is what is multiplied by flow. So if you have a flow, the diffusion will depend on the flow rate. But here we don't have a flow. So if I assign anything to dispersivity, its effect is going to be 0, because we're not going to have any flow from pond 1 to pond 2. But so we're gonna provide the diffusion somewhere else. So basically, I'm gonna go to water quality, and I'm gonna add this constituent. Okay, I'm gonna call the constituent what? Solute. Okay, so I'm just gonna call it solute. And then here, I can provide the diffusion coefficient. So this one is diffusion coefficient, right? And the unit, if you look, is cubic meters per day. Okay, so now you probably can change it to some other options, but I'm going to keep it as cubic meters per day. and I'm going to provide, let's say 0.1. Okay, so diffusion coefficient is 0.1, which is pretty high, but this is just a demonstration case. So that's a diffusion case for this contaminant. That's pretty much all we want. So we have now this constituent called solute, right? And the other thing I need to do is that I need to add some initial concentration. So what I'm going to do is that I will add solute to pond 1, but not pond 2. In order to do that, I'm going to select pond 1, and then you go to this item called constituent initial concentration, and you click on this, three dots, the box, and then I'm going to say, solute has a concentration in aqueous phase of 10. Okay, just an arbitrary number. And that's pretty much it. Now, the other thing is that I want to, diffusion is a slow process in general, so it's going to take some time. So I want to make sure that I'm going to get to the steady state condition. So then what I'm going to do is that I will just, increase the simulation time from 1 to, let's say, 5 days. Okay, let's now save it. Now everything should be ready right now, right? And okay, I have too many reminders. Okay, anyways, it's ready to go. I just run it. It's done. Now let's look at the concentrations. So I'm just going to go here, plot constituent concentration, and the only constituent I have is called solute. So I'm going to click on solute. Okay, not what I wanted. And then I'm going to do it here too. Okay, so this is the concentration in pond 1, pond 2. I can compare them to each other. Okay, I'm still far from reaching equilibrium. So what I'm going to do, what do you want to do to make sure that I'm going to reach equilibrium? I can actually increase the duration of the simulation to, let's say, 10 days or 15 days or so on. The other thing I can do is that I can go here and increase my diffusion coefficient to, I don't know, let's say 0.5. Okay, that's quite high. And then I'm going to run it again. So higher diffusion. Now this is what I'm going to get, starting from 10, getting to almost 5, and then this one, and then let's just copy one of them to another one to get a better picture. So that's what we get, right? So the concentration in compartment 2 increases, and in 1 decreases, and they get pretty equal to each other. Now, technically, they never become exactly the same. It takes forever, but they can practically become pretty, same as each other, or pretty close to each other. Okay, that's pretty much it. Okay.